Solve the polynomial inequality and write the solution set in interval notation. Now this polynomial is specifically a quadratic, so we're solving a quadratic inequality. Now our inequality has a greater than or equal to. The equal means that we will likely include any boundary values that we get. Let's take a look. First off, I solve the equation, because in order to find out when this object is bigger than 0, I need to know when it's equal to 0, and then look on each side of that value, or those values, to determine where it's bigger. This one factors 3x times x, and 1 and 4, and plus and minus, we have 12x minus x is our 11x, and our last product is minus 4. This gives us values x equals 1/3 and x equals -4. So our second step is then on a number line, putting these values down and testing. I'm going to test -4 first. In the initial inequality, this would be 3 times -4 squared plus 11 times -4 minus 4, supposed to be greater than or equal to 0. Now this value came from the equation, so this should make both sides equal. 16 times 3 is 48, minus 44, minus 4. Okay, not only does this show that they're equal, so this work was correct to get to that value, but it also happens to be true in the inequality. So this is going to be a solid dot, part of our final answer. Testing the 1/3. By plugging it into the initial inequality, we're now testing the inequality. We're done with the equation. We have that's 1/9 times 3 is 1/3 plus 11/3 minus 4. 1/3 plus 11/3 is 12/3, which is 4, and 4 minus 4, 0. Now it's true, and they match up, so this is the good solution for the equation, and it's a solid dot because it satisfies the inequality because of our equal sign. Now, to test the left, middle, and right intervals to see what the final answers are. We can do this in two ways. One, we can visualize the graph. Now the graph, if this were y equals this parabola, it opens up. This is the x-intercept information, so opening up, that would be our graph. And we're wanting to know where it's above or on the x-axis. So we should get that information. This interval should work. This interval shouldn't work. This interval should work. Now if we actually wanted to test these specifically, we would go in and pick a value left of -4, like -6. Pick a value in between, like 0. And pick a value to the right, like 2. And plug those in. So for the -6, it would be 3 times -6 squared plus 11 times -6. Minus 4, supposed to be greater than or equal to 0. That's 36 times 9. 36 times 3, which is 108. Minus 66 minus 4, is that greater than or equal to 0? Yes, it is. That verifies that that interval is good as far as it satisfies the inequality. 0, testing 0. So it'll be a little easier because of this 0. I always use 0 when I can. The only time I can't use 0 is if 0 is an intercept, a solution to the equation. That does happen. 0, 0, minus 4. Minus 4 greater than or equal to 0? Nope. That verifies that this part of the region, the interval, does not satisfy the inequality. And finally, testing 2. We get the inequality 4 times 3, 12, plus 22, that's 34, minus 4, which is 30, greater than or equal to 0? Yes, it is. That verifies this. So we have our solutions, the left interval, including the endpoint, not the middle, and the right interval, including the endpoint. So our final answer in interval notation, the left interval is from negative infinity to negative 4, hard bracket on the negative 4. Then there's a gap in between the interval that doesn't work, and then, so that's union, and then the right interval is from 1/3 to infinity. Now make sure you're not using the 0 or the -6 or the 2 in this answer, because the values that should be the boundaries are the ones we got from the solution of the equation. Also notice, because of the equal sign in our inequality, we very often use the bracket with the equal sign involved. All right, I hope this helps.